We are continuing our work with volumes, and we're still looking at solids of rotation. And instead of taking a region like this and rotating it about the x-axis, we're going to see what happens if we rotate it about the y-axis. Let's say our region goes from A to B on the x-axis, and the top curve here is defined by a function f. If we do rotate this region about the y-axis, then we end up with something that might kind of look like a football stadium if you think about it. We've got these walls here, we've got a hole in the middle because of how the region was defined, right? There's a gap between the region and the axis of rotation. And then inside it's kind of like a bowl, but with this hole in the middle. And as before, we're going to consider what happens with a representative rectangle when we rotate. As this representative rectangle rotates through space, it's going to make a cylindrical wall. To imagine this, this cylindrical wall here, think about if you had like a tray of Jell-O and you took a toothpick, stuck it into the Jell-O, and then moved it around in a circle. Now the idea is that this representative rectangle would start here as a little rectangle and then sweep out a cylindrical wall there, and then the next rectangle would sweep out another cylindrical wall, and so on and so on, and that's how the shape is going to be generated. And that's how we're going to think about the volume. So here's our cylindrical wall, and the wall has a thickness of, well, delta x, right? And it has a height of f of, say, x sub I. For the cylinder that we're looking at, there's a radius. And the radius is the distance between that rectangle and the axis of rotation. And it can be really hard to think about, well, what's that distance? What's that distance? It's x. It's the distance from the y-axis, because the y-axis, in this case, is our axis of rotation. Now let's talk about how we're going to consider the actual volume of the wall itself. Suppose I were to slice through the wall, like right here, and then unroll it completely. It would look like a big old rectangle. Or I should say a rectangular solid. It's got width, right? And that width right there is delta x. The height is, of course, f of x sub I. Neither of those is the tough part. The length of this entire wall would be based on the circumference of this circle. The circle has a radius of x. And so the length of this thing is 2 pi r, or I should say 2 pi x. Again, it's based on a circumference. So an incremental volume, or the volume of just this cylindrical wall, is going to be v sub I is equal to 2 pi x f of x sub I times delta x. Now if we're counting dimensions, x is one dimension, f of x sub I is another dimension, and then delta x is a third dimension. 3 dimensions give us volume. Now, as I said, we're going to envision this happening with a whole series of these rectangles, and we end up with a whole series of these cylindrical walls. Let's say we have n of them, and then we let n go to infinity. And that's, of course, going to lead us to an integral. What we're developing is basically a cylindrical shell. And so this is called the shell method. The volume of a solid obtained by rotating the graph of a function f for x from a to b, and a and b are both positive, about the y-axis is v equals the integral from a to b of 2 pi x f of x dx. Now, a really important thing, I think, to note here is that we're saying that f of x sub I is like the height of our cylinder. And x, is the radius of the cylinder. This formula is really based on 2 pi RH, which is the surface area for a cylinder. So that's the area of, say, the face of this rectangular solid. Okay. And then the rectangular solid has a width of delta x, a thickness. So let's say we have like 2 pi RH times the thickness. If you can remember 2 pi RH and then figure out what's the radius in each case and what's the height in each case, you've got this down. Just like when we were looking at the disk method, we were based on pi r squared times delta x. Or for the washer method, we were based on pi, say, outer r squared minus inner r squared times delta x. Those are based on the area of a circle, or subtracting the areas of one circle from another circle. Here we're looking at the surface area for a cylinder. And as we set these up, you're going to hear me say over and over, 2 pi RH. Let's see how this looks with a real-life example. Use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the y-axis. Y equals x cubed, y equals 0, x equals 1, and x equals 2. So here's our region in gray, and we're going to rotate this about the y-axis. I recommend always drawing all four of the, well, if you have 4 boundaries, I recommend drawing all of the boundaries every time because it's really easy to misidentify a region. And then draw a representative rectangle. It only needs to be, I mean, it doesn't need to be a fancy rectangle, just something like, in this case, it's vertical. And that brings to mind something really important. If we're using the method of cylindrical shells, then our representative rectangle should be oriented in such a way that's parallel to the axis of rotation. You may recall when we were looking at the disk or the washers methods that the representative rectangle was perpendicular to the axis of rotation, right? So that's the way in which these differ. That's how you know which one you're using. Now our volume is going to be an integral, and the bounds of the integral are the bounds of the region that we're talking about. And since our region goes from x equals 1 to x equals 2, those are our limits of integration. And then we're looking at 2 pi RH, and then of course there's a delta x. The radius is the distance between the axis of rotation and the representative rectangle. That makes this radius x. So in our integral we have 2 pi x. The height in this case is given by the function value y equals x cubed. So 2 pi x times x cubed, and then dx gives us a thickness, and that's what's going to give us volume. The actual integrating is almost nothing. This exponent here is 4, so we're looking at like 2 pi over 5 x to the 5th. Power rule there, evaluated from 1 to 2. Now we could go all fancy, but look, 2 to the 5th is 32, and 1 to the 5th is 1, so that's going to be 31, right? Times 2 is going to give me 62 pi over 5, and again, the calculus isn't so hard, it's the setup that's going to provide our challenges.